EE160, Chapter 5, Functions, Chapter 5 out of C, How to Program. So we've been going pretty strongly with these chapters so far, but starting Chapter 5, we're going to slow down. We're going to stay in Chapter 5 2 weeks. Yes, I can hear you all cheering in the background right now. There's a lot of material and examples, and this is the first chapter where we start worrying about actually developing algorithms rather than learning just the syntax of doing things. So, in this chapter outline here, I can see my screen's off a little bit, but in this chapter we're going to learn about functions. Basically, there are two types of functions, and then the rest of this chapter is more details about functions and some features of using both built-in functions and user-defined functions. So why do we have functions? Well, it's the divide and conquer principle. So most real-world programming problems are much, much larger than what we have done so far in this class. So we need to have some way to modularize the program, or in other words, break it up into smaller chunks. We learned looping functions already, which was and decision structures, but now we need to create functions to modularize our program. So here's some good programming practices out of your textbook. I thought that they were good enough that I should repeat them here. One is familiarize yourself with the rich collection of functions in the C standard library. So that is, once again, I've actually, oops, let me pull it over. Remember I gave you that C reference card on Laulima. That is a good starting place for familiarizing yourself with all of the different functions that are available to you in the C programming language. So some of your homework problems might ask you to do something and I haven't specifically covered a function. Here is a good place for you to start looking to get answers for these functions. Also, next observation, which is a good practice, avoid reinventing the wheel. When possible, use C standard library functions instead of writing new functions. For example, if I ask you to write a program that calculates sine x, don't write a program that through a bunch of iterative processes comes to some really high accurate estimation of what sine x is. Use the sine x function in the C standard libraries. Don't reinvent the wheel. So also using the functions in the C standard library helps your program. It makes them more portable, which portable means that they will work on more than one operating system, or sometimes people say more than one platform. Okay, so functions. I mean, you're back on our beginning slide. These are all like pictures of functions. You think functions in math, right? Well, it's very similar in many regards. So functions are called or invoked in the program, and in your program. So I've highlighted those words because those are important programming terminology words. So the function is called, and then the function returns the result. There are two types of functions, basically, on a high level in the C language. There are the prepackaged built-in functions. An example is printf. The main function is a function. Put character, get character is another one. We didn't do put character, but there's get character and put character. And sine x, part of your math library, sine x is a function. They are built in, part of C in the C libraries. What do you notice about a function? In each one of these function calls that I have printed over here, the examples, in each one, the argument, or either argument or parameters, which we'll explain in a moment, are in parentheses. And so printf is calling or invoking the printf function, and we're passing some argument to it. Then we have programmer defined functions, and I just made up one down below. It's one called calculate average, and it's going to get the average of two numbers, apparently. It would be my guess. So we have prepackaged ones and user-defined ones. Let's talk a little bit more about our prepackaged ones because we're going to use them a lot more. I've already mentioned this a couple of times now. Off of that C reference card that I posted on Laulima, there are math functions that come under the math.h header, which is a well, more about headers in a little bit. This is where all of these math functions are defined and reside. It's like a separate file called math.h where all the functions are defined. So you know you have your trig functions, and then you have some that we're going to be dealing with in this chapter that we haven't learned about yet, which is the ceiling, floor, and absolute value. So that's the one that we haven't learned about yet. So next. So here's an example of using one of the math library functions in C. One of the things that you have to do is at the top where you have your include statements, you include standard I/O, but also include math, and then you have available to you all those math standard functions. So this particular program prints a number raised to the third power, and it's done in a for loop. Notice I declare int s outside the for loop, so I don't have to use that extra flag in my compiler command. So it gets the numbers 0, 1, 2, 3, 4, and it finds the cube of the answer. And so let's look at the print statement for a minute, because some people I see might be a little confused by this. So I have the %i format specifier, which will substitute the value of s. The int value of s goes here. Then I have the escape sequence /t, which means tab. So in the output display there will be a tab. And then I have a .1 f for float, or a %.1 f for float. So this particular format specifier means show one place after the decimal point and output a floating point number. The function I used is power, so it's pow x, this is the base number is s, and the power is 3 right there. All of those math functions here, except maybe these down here, all of the ones up above here use data type double. So arguments and returned values are double. It says so on the C reference card. So even though I put an int for s cubed right here, it is going to return a double. So I have to use a %lf so that I can display a double with my printf command. So now let's talk about the programmer-defined functions and the parts of the function. So before we can define our own functions, these are the kind of questions we need to be able to answer. How do you give the data to the function? How does the function get used in the program? Or in other words, how does the function return the results? And how do you write your own functions? And then lastly, what are function prototypes? Okay, so defining a function. This is the format of a function when you define it. By defining it, I mean you're saying what this function does, and it can do a lot of things. You have to have a return type. That's like saying that the answer you're going to get is going to be an int, a double, a character, whatever the answer is that you're going to get. You have to say what kind of data type you're going to get as an answer. You have to have a function name, and then it has parameters. This first line of our function is called the function header. And then what the function does is in curly brackets, curly braces once again, and that's the function body. And examples will make this become clear. When you use the function, or your main part of the program calls the function, which is using the function, you just say function name and you pass what we say, we pass the argument to the function. Okay, these are terminologies right now and it will become clear. Up here it's a parameter, up here it's an argument. Just put that in the back of your mind. Naming our function. I said the function has a function name. Let's name our function. And there is some variation in styles for naming functions depending on where you look. Oops, I don't know what that's there for. And there are some rules for naming functions that everybody has to comply to. The styles that we will use is what is defined by your employer, or in this case, it's what's defined by our class, this particular class. When you name your function, it has to be descriptive, and it has to begin with a verb. Functions do something. They take actions. They perform something. So name your function with a verb. It needs to be camel casing, which I've already covered before. So the first letter is lowercase. Words in between have a capital letter in them. A function name cannot be a keyword, so you cannot name your function while. And the first character must be a letter. Can't be a number, can't be a special character first. But by the way, an underscore does count as a letter. I just don't care for using the underscores. But I won't forbid it. So the first character must be a letter. And I have a few good examples down below. Calculate equation. If I call that function, you can see that there are two. These are parameters in this case because it looks like it's part of my function definition. But anyway, okay. How does the function return a value? So here's a generic shape of a generic function called division. It divides two numbers, number A by number B. So my function name is division. It has two parameters, A and B, and when I call the function, I give the function arguments. When I define the function, these are the parameters of the function. And then it says I'm going to return a type double. So within the body of the function, I have to say return, and it's got to be something that calculates to a double value, and that will be the answer returned by the function to the main calling program. So now how do we use the function in a program? This is sort of a generic form of what a complete program might look like. You have your preamble up here. That's where you put your programmer name, date, and a description of the whole program. I just wrote preamble here because in the interest of space. Then you have your compiler directives. So include standard I/O, include math in this case. And then I have something else, which is a directive that I haven't talked about yet, but I'm going to introduce it here. I have a statement here that says define pi to be 3.141593. It's like a constant. Pi is a constant, so I named this variable. It's not a variable. I named this constant with all capital letters. Remember, constants are all capital letters. I defined it outside the body of the program, so the compiler makes space and defines pi before it ever goes into the program here. Whoops. Then we have the main body of the program, and I have it here as int main void. So but because it says I'm returning an int, I should have return 0 as the last line in the body of the program. So the body of our program is always embraced in the curly braces, but typically we do our declarations in what data variables and data types that the whole program's using. Typically we do that in the beginning. Sometimes there's a line of white space there, then you get the program body. Now this program body can call the function that it needs, but where you define the function is below the body of the program. So you see I'm outside the main now, and I've defined a function here. In this case it was called int calculate something, and it needs two arguments when it gets called by the main body of the program, and it will return, in this case it's x plus y. Okay, let's look at an example. I have an example. Write a program that converts degrees to radians using a programmer defined function. And just to refresh your memory, radians equals degrees times pi divided by 180. So let's go to our program here. Not that one. it's this one. So so I'm going to use standard I/O. I included math and I included pi. I know we need pi. I defined pi. Let's look at the body of the program. There's something here I haven't talked about yet, is the function prototype, but I have it in the area of where I'm making declarations. So what it is that you have to declare that you have a function called convert degrees to radians before the program can ever use degrees to radians. Why? Why is that? Because the function is defined after the body of the program. That's one of the big reasons why. So let's look at how we define the function, keeping in mind that it's past the body of the program. It's down below. My header, this is my header, says double convert degrees to radians, and the parameter that it needs is an x, and x is of type double. So I need to, when I call convert degrees to radians, I need to put a data type double here as the argument. So within the body of this function, I declared a data type, a variable called r, which in this case stood for radians. It's a type double, and I say r equals, r is assigned, it's an assignment operator, x times pi divided by 180, and then I return r. So r is a type double. I'm using r only locally within this function. It has no meaning outside this function. R has no meaning up in the main body of the program. But a argument will get passed to this function when it's called. So let's go back and look at the main body of the program. I have some stuff for the user. Enter angle in degrees. So then I use scanf. I get the user input. I save it in a location called angle. Then I print the result. Basically, I'm doing that. I'm saying so many degrees equals so many radians. That's the answer. Angle, that was the user's input angle, substitutes into that format specifier there. And then this format specifier gets the result of this function call. So I did a function right here. I called the function convert degrees to angle. I passed the argument, the angle argument here. The program jumps over here to the function, calculates it, and returns the result. I come back to this place, exactly where this place is. The result is returned, whatever the calculation turns out to be, and it gets put out in this format specifier. And then I have my usual press any key to end. This is what the program looks like when you, let me clean this up. This is what the program looks like when you run it. Enter angle in degrees, 45, enter 45 degrees equals this many radians. Whoops, press any key to end, and it already ended, so I need another get character. Notice how many points I have past the decimal. That's the default value. You can change that if you want in the format specifier. Okay, so recapping, this was the function call right here. When I call the function, the program actually jumps down here to where the function is defined, passes the argument, in this case it was 45, it passes 45 into this function, and then a calculation is done, and it will return a double value, 0.78 whatever, back to the program where exactly where the calling occurred. It will return back to there, substitute, put the right answer in here, and in this case that right answer gets put into that format specifier. Here's a snapshot of the whole program so you can see it all on one screen. So here was my directives to the compiler. Here is the main body of my program. Here is where the main body of the program called a function or invoked a function. Here is where the function is defined. When I call the function, the value that the user entered is passed to the function. That's the argument at that point. X is a parameter. 45 degrees is an argument that is passed to the function, but X is a parameter of the function. That's a confusing point for many people. But anyway, here's the whole program so that you can see it. So let's show you a few other things you can do with functions, some variations on it. Let's look at example in your textbook, the maximum function, user-defined function called maximum. So I actually have it here in Notepad++. I only need the standard I/O for this program. Okay, so they did something a little bit different, so I'm going to point that out. Here they did the function prototype above the main body of the program. That's okay too. I'll explain why it's above versus in the body of the program probably in a later video, because there's other features here about that need to be covered, why it's placed there. So by putting it there, it's the most powerful. But one thing to notice about it is that I have 3 parameters for this function, x, y, and z. And this is like a declaration of the function going on right here. Now I come into the main body of the function. This function is supposed to find maximum of 3 different numbers. So I know we're going to need number 1, number 2, number 3 that the user will enter. Here, notice how they did their printf statement. You can do it this way if you want. You don't have to. This is a string format specifier, so this phrase gets substituted in where that string format specifier is. I would have just used puts and put that phrase out there, but the nice thing about that, well, so many ways to do the same thing. And then scanf function gets 3 values, 1, 2, 3 values. They go in number 1, number 2, and number 3. Number 1 and number 2 and number 3 are the arguments to the maximum function call. So, and then here's what the main body of the program does. It calls the maximum function. Number 1, number 2, and number 3 are passed to the function, and your answer is given out right here. Then we go down below the main body of the function, and we define what the function is. This is where the function is defined. I define it as it will return an integer, and the 3 parameters are also integers, so it's expecting to have integers passed to it. One thing about noticing the function prototype, it's exactly the same as the header of the function definition, except that there is a semicolon right here. That's the only difference. Other than that, this line is exactly the same as the function definition header right there. No semicolon at the end right here. So this is actually the beginning of our first algorithm, an algorithm that finds the maximum of 3 numbers. Of course, we would like to extend that to the maximum of a list of numbers, but that's down the road. So what you do is you take the first number and you assume it's the largest. Then you compare it to the second number, but if the second number is larger, then that becomes the new maximum. And then, then you compare it to the third number, and if the third number is actually the maximum, then max gets redefined with the third number, and then you'll return the value of max. Notice it says return max, and an int is returned to the main calling program. This variable max right there is only defined locally. It only exists within this function. If I tried to say print max up here somewhere, it wouldn't know what max is. So max is only defined in this function. So I'm going to say a word here about the placement of the function prototype. In my degrees to radian program, I placed it within the main body of the program, which is okay. It also worked in this example from the textbook where we placed the function prototype before the main body of the program, before the main function. This is a more general case, having it outside, and it allows us to, if we had very large programs, to be able to interface to libraries and things that we would develop. They each have their place. Neither is right nor wrong, depending on the application. There are places where we want the more general case for it to be recognized by more of our broken down programs, and then you would put it here. So for purposes of this class, let's put it outside the body of the main, but keep in mind there may be reasons for it to be inside versus outside. Actually, for the size of our programs, it should be inside the body of the main, but this is, I guess, preliminary to thinking about it being outside the body of the main and having other libraries that we could be using. So let's do it that way, because that's what your textbook does also. So section 5.8 in your textbook talks about the header files, like we use the standard.io.h header file, we use the math.h header file. Those are another file located somewhere else in your system where all of the functions for that particular library are defined. For example, in the standard.io.h file, you would find how printf works and scanf works, and a bunch of functions are all defined in there. Similarly, for the math.h header file, you would find function prototypes for sin x, cosine x, ceiling, abs, etc. So we could also write our own header files, which is kind of the point of this section. Whoops. Of writing our own header files, but I think it's a little, to me, it's a little early to introduce writing our own header files, but we will later in the course. Actually, we do it more towards the end of the course when our programs are large enough that we might want to recreate our own header files. So for now, I'm going to say pass on this section because we don't need it yet. Our programs are not large enough that we would be creating our own header files at this point, and we're also not creating our own make files. So we will come back to this part later as our programs get bigger. Earlier in this video, I had this slide up talking about the already included functions in the math.h library, and it was the pow function that I had shown here for raising a number to some power. And then I mentioned that all of the math functions the arguments of those functions are type double, but then I put an integer here in this calculation, this function call. I put an integer in it of 3, but yet the result that was returned was still a type double, and I had to use the long float format specifier. Your textbook talks about it in section 5.6, function prototypes, a deeper look. But in particular, it talks about, I'm going to go back a few pages. It's slow, these ebooks are slow. It talks about argument coercion and the usual arithmetic conversion rules. Let me see. I'm getting there. You know, I should just do this. 5.6, function prototypes, a deeper look. So here we go, argument coercion and the usual error method conversion rules. In our case, I had a function and I put an integer in it and it returned a double type answer because all those math functions use doubles. So it did the conversion for us, so that your textbook calls this a coercion of arguments, i.e. it forces the arguments to take on the appropriate type. So the math library function square root, for example, can be called with an integer argument even though the function type prototype says it's a double, and the function will still work correctly, and I showed you that working correctly when I used the data type, when I used the POW or the power math function as well. That's what this whole section is about. It will promote something to the highest precision also within the function. And then I mentioned that if you're using double, the scanf conversion specifier is LF. The printf conversion specifier when you're using double is an F. Long double is capital letters. I'm happy with double. And floats are F and F in both cases. The main one is that double has a slight difference when you're using scanf versus printf. That'll be a gotcha for some people. So let's take a look at some of those math functions in the math library that you may use as a result of including math.h header file there. And remember, these functions have function prototypes declared in a math.header file somewhere. I'll have to show you that. Anyway, so here's a few functions that I'm going to show you. One is the absolute value function. So if I put in absolute value -5, notice I put it in as an integer, but it's going to be coerced into a double. And then if I want to show it, I still have to keep in mind that it's going to be coerced into a double, so I have to use LF as my format specifier. My 0.3 means I'm going to show 3 numbers past the decimal point. So sure enough, the absolute value of -5, even though I entered it as an integer, but it's coerced into a double, I show it as a double, is 5. This next function is the ceiling function. The ceiling function takes your floating point number and rounds it up to the next whole integer. So 9.2 rounded up to the next whole integer is 10. It is again displayed as a floating point number. It's a double. The floor is the opposite of the ceiling. The floor will round it down to the lowest in the integer, next integer. So 9.2 rounded down would be 9.0. And then I did a trig function. I did your sine function, and I put pi in here. So sine of pi is 0, of course. But the main thing is that the argument of the trigonometric function is in radians, not degrees. I cannot put sine 180 in here. If I'm looking for this 180 degrees, I would have to convert it to pi. So this argument, whatever argument you pass here has to be in radians.